Welcome you all for the video lecture on the problems of the module 1 of the analog circuit course. Okay, fine. Okay, ma. Okay, so if you see, let us first have the discussion with the DC analysis of your BJT. Okay, first is DC analysis. Okay, and another one is next is the AC analysis. We'll see. So AC analysis doesn't deal with only AC analysis, because AC analysis, when we do AC analysis, obviously we'll be dealing with DC analysis also. Okay, fine, no problem. Now first let us see about the biasing. Okay, biasing of your BJT basically. Is that okay? So in this biasing techniques of BJT, I will just take only very simple biasing with the direct batteries. We'll see first one, and then we'll see specific biasing techniques, and then we'll go for AC analysis. So this is the flow of the video lecture. Is that okay? Fine. Now look at this one. In this problem, we can see VCC is given as 10 volts, which is directly given to the through the resistor. They are given it directly to the collector, and here with the VBB 4 volts directly given to the base, and emitter is grounded. So we need to find out. They are asking us to find out the power dissipation. Am I right? Which is nothing but PT. Power dissipation, which is nothing but power transistor power dissipation basically. Okay. So now in this case, all values are given to you. RC is given, RB is given. So we need to find out IBQ, okay, and VBEQ, and ICQ, and VCEQ, and determine the power of the transistor, which both of this put together will be your power dissipation. Okay, as you see here, VBE, IB, VBE on plus IC, VC is put together as the total power dissipation. But mostly if you see, this is almost negligible, so we will keep almost equal to PT is almost equal to IC, VCE. Okay, so now it's easy to find here. It's a very direct method here in this case, direct method, where in this, if you put a loop inside the loop KVL, if you put, so what you have here is, you will have a VBB 4 volts, so 4 is equal to IB RB plus 0.7 volts. That's it, 0.7 volts. Okay, so IB can be written as 4 minus 0.7 divided by RB. Okay, similarly IC also you can do like this. Okay, you can do and solve it like this. If you know VCE, so VCE is not given to you. So if since VCE is not given, we will use the formula IC is equal to beta IB. Okay, so we will find out ICQ and VCEQ. You can easily find out, which is where this minus this drop will be equal to the VCE. So with that we can find out, and we can say that our power transistor PT is equal to 3 into 3 IC is equal to 3 milliampere, 3 into VCE, which is nothing but 4 millivolts. So what we can have is 3 into 4 millivolts. This current is 3 milliampere, so it's 10 power minus 3, so it is almost equal to 12 milliwatt. That's your power dissipation. Fine. Okay. Now coming to the next problem, where it is it's the same problem, except that you have one RE resistance alone has been included here. Okay, and it is also dual supply. Okay. Now the values given for you is VBE on is 0.7 volts, that is already known, and beta is 75. So these are the two things is been given to you. Okay. Now again same thing, apply KVL here and apply KVL to the output loop. You can find out IB here, and you can find out IC here, and once you find out ICQ, and we can find out VCQ. So our aim is to find out IBQ, VCEQ, and ICQ. That's the characteristics, because they are asking you to find out the characteristics in this equation, in this circuit, in this problem. Okay. So now tell me, what is your VBB? very easy. VBB is equal to IBB minus VBB is equal to IBRB plus VBE plus IERE and V minus. Okay, so putting it all together, then you can find out IB. So IB is nothing but VBB minus VB on minus V minus. Okay, so there is one change that we can make it, since it is IE and two different parameters are there, we can write IE in terms of IB, which is nothing but beta plus 1 into IB. Okay, so that's what comes up here, like RB plus 1 plus beta RA. Is that okay? So and find out your IBQ. So IBQ is mostly will be in terms of micro amperes. And then you have IC, which is nothing but beta IB. So find out the value for that, directly substitute and find out. IE also you can find out. So all known, IC is known, IB is known, and IE is known. So now you can apply the KVL to the outside loop directly. Find out what it is. So there is one clue I will give you, because both the supply volts are like this. We can just add the supply voltage and say we have 3.6 volts. Okay, so 3.6 volts is equal to IC RC plus VCE plus IE RE. What is your VCE here then? VCE is, we can write one more thing. The IE can be written as IB into beta plus 1, where IB can be written as IC by beta. So the entire term becomes IC into beta plus 1 by beta. Okay, it becomes like that. So substituting that one here, what you have IC, we can take it out. So VC is equal to 3.6 minus IC into beta plus 1 by beta into RE. Okay, substitute that one, you will get VC is equal to 3.6 minus IC into 10.0. IC is basically 0.02 milliampere, so you will get 0.02 into 10.04. You put it will be in terms of milliampere, 10 power minus 3. Okay, so we calculate that one and you can find out the answer of how much you have. Okay, fine. Is that okay? Now this is an exercise given to you. So using the previous examples, we expect you to complete this one. Okay, the slides will be uploaded in the MS Teams, so try to complete it and submit it as an assignment. This is basically comes as a DA1 for you. Okay, DA1. Okay, this is basically one part of DA1. So there are many exercises are there. You can see that one. Fine. Okay. Next one is basically using a fixed voltage regulator. So again, same principle. So instead of having three different supplies, you have only one supply and the other one is grounded. So apply KVL here and apply KVL here and determine your current and voltages. That's how we basically do. Okay. So VCC is equal to 12 volts here. What we have here, and ICQ. This is ICQ. ICQ is almost 1 milliampere, and VCEQ is 6 volts. Okay. So now, since VCEQ is given and VCC is there, and ICQ is given, you can first thing you can do is you can find out RC straight away, because if I apply KVL, it will become VCC is equal to ICRC plus VCEQ. Okay. So IC is given 1 milliampere, 1 into 10 to the power minus 3 into RC plus 6 volts, and in the left side you have 12 volts. Okay, so I would say it will become 12 minus 6 divided by 1. Okay, and since it becomes 1 into 10 power minus 3 here, you can write as 10 power 3. So it becomes 6 kilo ohm for you. Okay. So now once you know this one, RC is known, then IB also can be found using this formula, because IC is already given to you. So ICQ by beta, because beta is already given in the problem. No, it's not given. I think probably you can assume it. Assume the beta to be 100. Okay. So 1 milliampere by 100 is basically 10 microampere. So IBQ is known now. Now once this IBQ is known, obviously we can find out RB. So RB is basically what? VCC minus VB on divided by RB, divided by IBQ. Okay, so you will have 1.13 mega ohm. So your input resistance will be more, because your IB current is very less only. So IB 1.13 mega ohm you will get. Fine. Now, if I keep, changing the beta, okay, and find out what is my ICQ and VCQ. If you find out, I can see that for this particular circuit, obviously, it keeps varying. So it is not a, very stable one. So stability is very poor in this. Okay. Okay. Now coming to the next problem. So let us take a voltage divider bias circuit. Okay. So sometimes circuit will not be given in your problem. So you must be able to remember that. So basically, how the circuit will be, you will have that's how the circuit will be. Okay. So that's your VCC, and I'll just round this one. So this is R1, R2, RE, and RC. Is that okay? So now they are given you everything. R1 is given, so it is 56K. R2 is given 12.2K. RE is given 0.4K, and RC is given. RC is given 2K. RC is given 2K, and VB on, obviously it is 0.7. Okay, and yeah, so beta is also given. Okay, VB on is given. Everything is given. VCC is 10 volts. Okay, so they are asking you to find out the Q point variation. Okay, so now any voltage divider bias like this at the input side have to be converted into a Thevenin's equivalent. Okay, so for a Thevenin's equivalent, basically what you have is VTH and RTH. Okay, and you will have emitter resistance there. This is for the input side loop. So RTH and VTH, and this is basically RE. So how do you find your RTH? VTH and RTH. Thevenin's equivalent, basically between this and the ground, basically. Okay, this and the ground. So in order to do that, you can use a voltage divider rule. Okay, so voltage divider rule states that voltage across the resistor, because the VTH happen to be the voltage across the resistor R2. Okay, so that means R2 by R1 plus R2 into the input voltage VCC. And in order to find the RTH, what you do? You ground the VCC. So if you ground the VCC and see what will happen, R1 and R2 will become parallel. So R1 R2 in parallel. Okay. So straight away you can find out RTH. Straight away you can find out VTH. Substitute that one. And coming to IBQ, IBQ is basically the current flowing through the resistor RTH in the loop, basically. So I have told you already that when you look resistance from here, it is nothing but beta plus 1 times of RE, because of the current ratios and because of the equations that we see from here. Okay, if you see from the other side, it is divided by beta plus 1. From this side, it is beta plus 1. Okay, so putting that one, what we have here is IB. Just excuse me. So that's by IB. So the entire resistance seen here is beta plus 1 RE. Okay, so voltage divided by the resistance. What are the two voltages that I have? I have VTH here and VBE. So VTH minus VBE on divided by RTH plus 1 plus beta RE, because RTH and this one will be in series. Both will be in series. Okay. So now from this we can find out your IBQ. Is that okay? Fine. Now the collector current, obviously you can use the formula ICQ is equal to beta IBQ. With that you can easily arrive at a value of 2.16 milliampere. And emitter current, obviously we know that it is nothing but 1 plus beta IBQ. So with that you can easily find out 2.18 milliampere. Okay. And at the output side, output loop, you can obviously straight away you can do a KVL here. Okay. So VCC minus ICRC minus VCE. VCE is also there. Don't miss out the VCE. Then IERE. Okay. Put that one here. The VCE is equal to VCC minus ICQ RC minus IERE. So find out the value straight away here. Okay. So in this case, if you see, even if you change the beta value, okay, of the transistors, you can see there is not much change, very minimal change only. Okay, especially when you look at your IC, 1.8 milliampere, 2.6 milliampere, 2.16 milliampere, and 2.32 milliamperes only. Okay, so it's basically very stable. IC is very stable with respect to the beta. Okay, fine. Let us get into the next problem, where I am going to use a PNP transistor here instead of NPN. In all the other cases, I used PNP. NPN I have used. So in this case, I am going to use PNP. So it is basically a PNP circuit, and we basically want to find out the quiescent voltages. Okay, fine. So this is nothing but my VECQ. Okay, VECQ. And this is nothing but VEBQ. Okay, and ICQ and other things remains the same. Okay, and VRE1 is 1 volt is given to you. And the best part is there is no values of resistors given to you. You have dual supply plus 9 volts minus 9 volt, dual supply is there. The first thing that you can do is that when you see a circuit like this for a DC analysis, this again DC analysis only, we are not doing any AC analysis here, only DC. Okay. So in this DC analysis, what you do, obviously you will open circuit it, all these things will be removed. Okay, so we are left with only this circuit, R1, R2. So now we need to find out VTH from this to the ground. Okay, so in this case it is not across R2, so it's between this point and the ground point. So basically what happens is, like, if you see, you will have 9 volt supply here, okay, and you will have R1, then you have a point here, then you will have R2, and that is connected to, this is basically grounded, and this another connected to plus or minus, this is again a 9 volt which is connected to this. So this is R2, this is R1, and this is nothing but my VTH point we need to find out. Okay, VTH between these two. So we can use a superposition theorem. So consider one source at one time and find out your VTH. So if I say that if top 9 volt is there and bottom 9 volt is grounded, so that means VTH will become the voltage across the resistance R2. So it will become R2 by R1 plus R2 into 9 volts. Okay, and if I say that top one is grounded, then it becomes VTH is nothing but the voltage across the resistor R1. So it becomes R1 by R2 plus R1 into the other 9 volts. Okay, so like that you need to find out your VTH. But if you ground both the sources, you will have R1 and R2 parallel. Okay. Okay, so now if you reduce that one, it will become, the circuit becomes like this basically. Is that okay? So now only one assumption that we are making is beta is 80 and VBE on is 0.7 volts. Okay, these are the two things that we need to consider here. Okay, fine. VBE on they say, or VEB on, whatever that you want to say, you can say it. Okay. Okay, ma'am. Fine. Now VTH, I will show you the final value of the VTH here. So VTH comes as R2 by R1 plus R2. This is R2, sorry. R2 by R1 plus R2 into V plus minus V minus plus V minus. This is the final formula I am getting. Okay. So now I can express this one as 1 by R1 into R1 R2 by R1 plus R2. Okay. So there is a reason for the expressing like this, because we don't know any values of the resistors. So we need to arrive at some solution. So that's the reason I am expressing this as Thevenin's resistance itself, R1 R2 by R1 plus R2. Okay, that's the only thing. So now VRE is equal to 1 volt and ICQ is equal to 0.5 milliampere. This has all been given. Okay, then what will be RE? RE is nothing but this one basically IE only flowing through this. How can I then find out? IC basically you can write as ICQ is almost equal to IEQ, we can write. Okay, if that's the case, the voltage is 1 volt, so 1 divided by 0.5, I can take it as 2 kilo ohm. So RE is found now. Good. So RE is found. Now let me write RTH as R1 R2 by R1 plus R2. Okay, or I can write it as, if you see, RTH is R1 by R2, or I can write it as, if you see, RTH is nothing but RE by into beta plus 1. Okay, I can write like that. Okay, sorry, I made a mistake here. Because I'm looking from this side of the loop, so it should be multiplier, it should be multiplied of that. Okay, sorry. So I write it as like this. Just a second, huh? So, okay. So RTH is equal to RE divided by 10 into beta plus 1. That's how it is. So when you look, excuse me, when you look from here, obviously the resistance is beta plus 1 times RE. But what they basically say that it should be at least 1 by 10th of the RTH is basically 1 by 10th of the RE basically. Okay, that is 0.1 into beta plus 1 RE. That's what is given here. 0.1 into 1 plus beta RE. Okay, so that is the RTH value. So I can straight away write and find out this one value, and then VTH is nothing but 1 by R into RTH. Okay, RTH into 9 minus or minus 9 plus minus 9. So obviously this becomes basically 18. Because 18 into 16.2, we can find out that one, and minus 9 comes like that. So that's my VTH. So why I'm having this one is, excuse me. So what we have here is that when we put an loop current, KVL in the EB loop. EB loop is here. This is the KVL, this is the EB loop. That's my EB loop. So V plus IE RE plus VEB plus RTH plus VTH is equal to 0. Okay. So, or in other words, how will I write? V is equal to IEQ RE, VEB on IBQ RTH and VTH. So this is where I need RTH value I know, VTH value I have barely found out. So IEQ I can easily find out. IEQ is equal to 1 plus beta into IBQ. Okay. So now put all those things together here. V plus is equal to 1 plus beta IBQ RE plus VEB on plus IBQ RTH plus VTH. So from this basically what I can do, I can find out, since ICQ is equal to 0.5 milliampere. Okay. I can directly find out IB because beta is known, means I can easily find out that one. Okay. Otherwise, what I can do, I can solve this one and easily find out what is IBQ also. But anyway, leave it. So I will find out since ICQ is 0.5 milliampere, and I have beta given as beta is not given in this form. Yeah, beta is 80 that we have already assumed it. So with that, I can find out what is IBQ. Okay. And then we can write it as 9 minus all those things you can write. So why I am doing like that? Because I will have only one unknown, which is R1. Okay. So with this I can find out R1, and then I can find out once I found out R1, then RTH equation is R1 parallel R2. That is RTH is equal to R1 R2 divided by R1 plus R2. So from this I can easily find out R2. Okay. R2 can be found from here. So then ICQ is known. IEQ is also can be easily found because we know that IEQ is 1 plus beta IBQ. Okay. So IEQ is also known. Okay. Now in the output loop, EC loop, if I put, I'll get V plus is equal to IEQ. So basically, look at here. This is a loop. So V plus is equal to IERE plus BEQ plus ICRC. Plus this one. I basically say that plus 9 minus 9 plus 9 minus or minus 9 is basically 18 volts. So 18 volts is equal to IERE plus VEQ plus ICRC. So that's what we are putting here. So 9 is equal to, so they are putting 9 here because we can bring the 9 here and put it together as 18 volts and then write it as IEQ RE, and then VEQ, and then ICQ RC. That's what it is basically. So you will have RC as 20 kilo ohm for this. RC is the only unknown here. Fine. So this is how you solve the problem. If they are asking you to find out the resistor values, the resistor values are not given to you. Okay. Fine. Next problem is again this is for your DA2. Okay, so the first one I have given you. Now this is the second one. So try to complete this one. This is again a similar problem only. Answers are given to you. So verify that whether you are getting the answers properly or not. Okay, fine. Let's move forward. Okay. Now let us go ahead with the small signal analysis. Okay, so let us find out the small signal voltage gain. When I say that small signal voltage gain, mostly or you should find about only mid band gain. Okay, the mid band gain we call it as. Okay, fine. Yeah, mid band gain. Mid band gain. So in some of the problems it may not be given, so but you should be able to understand this one. Okay, so now there are some assumptions there. Beta is equal to 100, VCC is equal to 12 volts, VB is 0.7, and RC is 6 ohm, and RB is 50K, and VBB is equal to 1.2 volt. So this is the circuit for you, given to you. So VBB is given as 1.2 volt. This is your AC, this is your DC, and this is your AC source, an AC signal basically. And you have RB value is given, beta is 100 is given, and VCC is given as 12 volts, and RC is given as 6K, and RB is given as 50K. RB is given as 50K. So now first what you do is perform the DC analysis, and then you can go for the small signal AC analysis. Okay. So when you do for the DC analysis, what you do, you basically short the AC. No AC is available. Fine. So once that is done, obviously then you will know easily what to be done. So you have to apply KVL to the inside loop and KVL to the outside loop. Find out all the values of IC and VCEQ. So in this case, VCEQ is assumed to be 6 volts, because generally what we see here is VCE is always half of VCC. Okay, so 6 volts if you assume, then you will have ICQ is equal to 1 milliampere. So R pi you can straight away find what is R pi? R pi is basically beta by GM. So GM is basically ICQ by VT. Substitute here, you will have beta VT by ICQ, and you can find out all the values are given. So straight away find out the value, it is 2.6 kilovolt. So similarly GM ICQ by VT. So VT always it should be 26 millivolts basically. So just understand that. Okay, mostly room temperature only you have to find out, unless otherwise it's specified. Okay, so what you have here is 38.5 milliampere. That's what you get. Now if you apply KVL to the inside loop, you will have IB equation like this, IC you can find out like this, and KVL at the output loop you will get this one. Okay. Okay, now this is what it is. Now let us draw the small signal model, and we'll find out the mid-band voltage gain. Okay, so small signal model is basically for the transistor. Let us draw the transistor first. Emitter is grounded, so I will have R pi between base and the emitter, and between the collector and the emitter I will have a voltage dependent current source. So I can write as GM V pi. Okay, so V pi is the voltage across R pi, and this is what it is. Okay, now let us look at what all the resistors connected here. So at the output side, from the collector I have one resistor connector. So this is basically a small signal analysis. So what I will do is I will basically have to first short the DC. Okay, all DC should be grounded. Okay, no volt here, and AC also no AC here, no DC here, DC VCC grounded. So now what about your RC? RC is between collector and the ground. So RC is between the collector and the ground. So that's your RC, and a V0 is obtained across this. Okay. Now at the input side you have RB and Vs. So RB and Vs. Okay, that's your ground. Now how will I find out the voltage gain? V naught, this is my V naught. So basically the current flows here at the input side, and at the output side current flows this way. So I can write V naught is basically minus Gm V pi into Rc. What is your V pi here? V pi is, you can use a voltage divider rule. V pi is basically R pi. V pi is the voltage across R pi, so R pi by R pi plus Rb into Vi. So what is the gain? V naught by Vi is equal to minus Gm into R pi by R pi plus Rb into Rc. That's your voltage gain formula. Okay, you should be able to easily solve this one. Okay, so substitute all the values. All values are there. Substitute all the values. You will have minus 11.4. This is the voltage gain. Okay. So what we say that it is, it basically tells us that it is 11.4 times the input voltage. Fine. Now let us go to the next problem. So in this case, again they are asking to find out the small signal voltage gain. Again it is mid band. Okay, and they are asking to find out the input resistance also. Okay, and beta is given as 100, VB is given as 0.7 volts, and VA is infinite. Okay, VA is infinite means we basically what we say here is that your your R naught is basically infinite basically. Okay, R naught is basically infinite. So no output resistance of the transistor must be considered here. Okay. Now since so we can look at the circuit here, the external capacitors are there. So for our analysis, since we are doing mid band, the capacitor will be short. Okay. So first you do the DC analysis. So in the DC analysis, what you basically do, you will we will basically open circuit the capacitor. So when you open circuit it, all this will go. Okay, so only thing this is remaining. Okay, so what you basically do, you then find out VTH, RTH. So your circuit has to become like this: VTH, RTH. Then your transistor like this it comes. The emitter resistor comes like this. Then you will have RC. So this is RC, RTH, VTH, RE. That's your equivalent circuit for your DC basically. So find out VTH, RTH, all those things we have seen earlier in the previous problems. So find out everything and find out R pi also you need to find out, GM also we need to find out. Okay. Now let us look at the AC analysis. So in AC analysis, what you basically do? In AC analysis, we short the capacitance for the mid band gain. Short the capacitor, no capacitance, and the DC will be grounded. Okay, and then you have to redraw the circuit in the small signal model. So first you draw the transistor. So that's your base, collector, and emitter. So in this case, emitter is not grounded; it is connected through a resistor RE. So RE should be there. Okay. So now this is R pi, and this is RE, and this beta IB. I write it as beta IB because of some reason. I'll tell you. And from here, collector side, you see collector, from the collector, RC is grounded. So from the collector, RC will be grounded. That's my RC. And the V naught comes from here basically. That's my V naught. Okay, at the input side what happens, like I have R1, R2 and I have RS. Okay, so I will have R1, R2 parallel, I will have only one resistance here. I'll write it as R in, which is nothing but R1 parallel R2, and then I will have one RB, RS or whatever that source resistance, okay, and then I will have source. This is my Vs, and this is my Rs. This is R in, okay. So now what I can find out the formula straight away. What is my V naught? V naught is basically, see, V naught is the current flowing through the current flowing, V naught is the voltage across the RC, okay. The current flowing through is beta IB, so it is basically minus beta IB into RC. So if I know IB, then I can easily find out what is my V naught, okay. So that is the reason I have writing it as IB. Why it is so? Because the current flowing at the input side is basically IB. This is R pi. Now what is the current flowing through RE? Basically this current plus this current. Okay, so this is nothing but IB. This is nothing but beta IB. So the current, sum of the current flowing through RE is nothing but beta plus 1 IB. Okay. So now, what is my V in? V in is the voltage across this resistor Rn, which is nothing but the voltage drop across R pi, okay, the voltage drop across R pi and the voltage drop across Re. Because both are parallel resistance here, obviously the voltage, sum of the voltage across R pi and Re will be the voltage across this Rin, and that will be your V in. So I can write V in as R pi, okay, as voltage across R pi IB R pi plus IB into beta plus 1. So what is V in by IB then? R pi plus beta plus 1. This is beta plus 1 Re, it should be, okay, Re. That's your basically your R in resistance. What is your Ri then? Say if I say, no, I would say that this is not R in, RIB. I can call it as RIB. So basically this is RIB. And what is this Ri then? Ri is basically R, yes, sorry, not RS, sorry, RIB. R in, okay, plus RIB. R in plus RIB is your Ri resistance. Okay, so you can find out the value here. RIB is this much because we know that it is R pi plus 1 plus beta Re, so that is your input resistance. And the overall input resistance is nothing but Ri, which is nothing but R1 plus parallel R2 plus is RIB. Okay. Oh, sorry, I made a mistake here. It should be not plus. This is in parallel actually. Okay. Because both are in parallel. This is parallel with this one, obviously. Okay, both are parallel. So R in parallel, RIB. So that's your Ri. So we have found everything here. Now straight away, and before that you can find out your R pi also using your DC values, Vt V by ICQ, Vt beta by ICQ, and Gm is equal to ICQ by Vt. And this is anyway infinite. Okay. So now we can substitute these values that V naught I am getting now. So what will be my V in the other sense? V in, how will I write V in is equal to Vs is applied voltage into R in divided by, okay, R in divided by, or I can write it as Ri instead of R in, I can write as Ri. Okay. Erase. Anyway, because its voltage is across, anyway it is the same thing only, so I can write as Ri divided by Rs plus Ri. That is Vs basically. Okay, so we can substitute this one here. In substituting in this equation basically. Okay. This equation you can substitute and find out your IB parameter. Okay, so IB parameter you can find out, and then what you will get basically. So it will be, you will basically get I don't have a place to write here, so anyway I will write it here. Finally I will write it here. So you will basically have AV as minus beta RC divided by minus beta RC divided by so I write it like this: Ri divided by Ri plus Rs. This is our second equation, and this is R pi plus beta plus 1 into Re. This is the voltage gain equation that you will get when you substitute all of those things. Okay, so when you substitute all the values here, you will get a voltage gain of minus 4.3, and approximately if you want to find out, AV will be equal to output resistance by the input resistance, which you will get 5 minus 5. Okay, so this is how you solve the small signal model with emitter resistance without any bypass. Okay, so practice problem 3, this is for your DA1 again, so I want you to do this. Fine. Okay, very simple one. Similar one earlier we have seen. So this is basically the AC equivalent, and if you short this one, obviously it become DC equivalent. Okay. So you can find out, they are asking you to find out the small signal gain. Okay, so small signal gain means again it's mid band. Small signal gain GM, R pi and R naught. Okay, fine. So this is basically a PNP transistor that you have to note down. It's a PNP transistor, PNP. So that you have to note down here. You can easily follow anyway one PNP transistor which can already be solved for you. Okay, good, fine. So another practice problem is there. This is again you can use it for DA1. So for another almost 4 problems we have given. So we can use it. This is almost the same one which we have seen earlier in the previous example. Okay, very similar to that. Okay, except beta value will be changed and RC and all these values are different. Then let us come to the next problem where we need to find out the corner frequency. So what is corner frequency? Basically, it is a frequency response kind of a problem. So you have it's the same problem like the earlier one. Earlier one CC was there, but CC value was not given to you, so you are not expected to find that. Now it is given to you. You are expected to find out this. Okay. So this is basically coupling capacitor. So we need to find out the frequency response due to this particular capacitor. Okay. So now first you do the DC analysis. So for the DC analysis, you will open circuit this completely. So all the circuit will go. So only this is remaining. So you put a KVL at the you will basically have to convert this into the VTH, RTH, those parameters you need to convert it, and you will have the resistors like this. So basically it is basically RTH, RE, VTH, and then you will have a RC resistor there. Okay. So find out your IB and IBQ, VCE, VCQ, all those things you can find out, and also you can find out your GM and R pi. Very important. So because for your small signal analysis we need this. We need this for your small signal analysis. Okay, fine. So that's your DC analysis over. Then after that, straight away, what do? You have to go for finding out the mid-band voltage gain. So for the mid-band voltage gain, what do? Basically short circuit your capacitor and then draw the small signal equivalent model, which I have drawn in the previous experiment. I think it's there. Yeah, it's here. This is the one similar to this one. Okay. This is for another problem, but similar to this one only you will get basically. Okay. But in this case, you don't have load capacitance. Other things are not there. But I think you can refer to the earlier one. This is the one. It should be like this. Okay. So once it is like this, obviously you can use the same problem which I have shown you earlier, which is nothing but GM R pi RC by RSI plus RI into RB by RB plus RIB. Okay, and yeah, of course, yeah. Same thing, GM R pi is nothing but our beta here. That's your beta. Beta RC, same formula which I gave you earlier. Okay, exactly the same because there is no change at all. Fine. Okay, now how will you find out your corner frequency? Okay, so once you have finished your mid-band gain analysis, what you basically do, you have to basically go for the frequency response analysis. So what do you do basically? You open circuit this one. Okay, open circuit this one. Try to identify the sum of the resistance, because the equation is basically FCC is equal to 1 by 2 pi R equivalent C. So what is R equivalent here? Basically that's what you have to find out. CC basically. R equivalent is basically what? RSI plus the resistance seen here, RI. So I can write it as RSI plus RI is your CC. So what is RI basically? RI is basically what we have here is Rin, that is R1 parallel R2, R1 parallel R2 parallel beta plus 1 Re. I think we need to have R pi also will be there. Okay, so that's your Ri. Okay, so substitute, once you know all those things, substitute this one. You can see here, this is what is been here. Okay, so you will find out 6.77 kilo ohm is your input resistance. Okay, so once you have done that one, then find out your FL straight away. So 1 by 2 pi. My R equivalent is this is tau S equivalent is RS plus RI into CC. So inverse of that is your basically 1 by 2 pi tau S is your frequency. Okay, fine. Now that's all over. Now then load capacitors. There are two capacitors are there in this particular problem. So I will show you this how to do that. Okay. So what is the equivalent for your FCC? This we have seen it in the previous experiment. So it basically is 1 by 2 pi R SI plus RI into CC. Okay. So R, that's your RI and all, we know it. We have seen it in the previous case. Now look at this one. If you open circuit this and look the total resistance from here, what will be my what I can say FCL? 1 by 2 pi. The resistance both are in parallel actually, because you will ground because AC analysis you will ground the DC. Okay, so RC and RL will be in parallel. So RC parallel RL into CL. That's your other cutoff frequency. So two frequencies are there. You can directly write it, determine the two frequencies. Before that, you have to do the DC analysis and all those things. That you have to do it always. So you take any circuit like this, first you have to do the DC analysis, then you go for the AC analysis. In the AC analysis, you can first do the frequency straight away, because straight away that is already been known to you, all the values straight away you can do that, and then go for the mid-band gain analysis. Okay, fine. Okay, so now once you have known that FL and FH, FL is due to the coupling capacitor at the input side. This is due to FL and this is due to your FH. So you can draw the graph like this. Fine. So why we say that, you may have a doubt why we have, because this is not internal capacitance, this is a load only, no? So load capacitance generally it will basically affect the higher frequency component. Okay. Okay. Now the next one is your multi-stage transistor circuit. So multi-stage transistor circuit means basically we will have two stages instead of having one single stages. So single stages we have seen everywhere. All these examples you have seen is only single stage. Now multi-stage is basically, this is your first stage, you can see here. It's your first stage, and that's your second stage. So it's stage 1, and this is stage 2. Okay. So now when you do the stage 1 and stage 2 analysis, basically what you do is first you do all the DC analysis of the first stage separately, and then you go to the second stage separately. Okay. So now I will show you that one here. So now look at this one. So this is the DC analysis circuit. So you can see here IR1 is flowing, IE2 is flowing, IB2 is flowing over here because this is a PNP transistor. You can see here, this is NPN and this one is PNP. Okay. So the current which is flowing from here, it flows like this basically. Okay. So these two currents entering in forms your IC1. Okay. Then IB1 you find out, IE1 you find out, and then IR1 you find out, then IE2 and IC2. That's how you need to find out. Okay. So RTH first, obviously at the input side, you are finding out VTH into RTH, because that this particular thing you can reduce it with VTH into RTH. So that you find out VTH, what is VTH, what is RTH, you find out. Then base emitter loop of Q1 you do, okay, and then find out what is IE1. There's only one missing parameter is IE1. Okay. Okay, fine. Yeah. Sorry, I think yeah. Correct. What you do is basically since IB1 is the missing parameter, we'll replace IE1 with the equivalent formula I1 plus beta IB1, and then find out IB1 first. Once you know the IB1, then you can easily find out what is IC1. We know that, okay, because IC1 is equal to beta IB. So beta is given to you the transistors. Obviously beta, yeah, it's 100 only is given to you. Okay, so its beta is 100. So if it's not given to you also in the problem, you can assume to be 100. Okay, 100 is given. So find out that one because it is basically into 100 is nothing but your IC basically. Okay, then IE1 basically, how will you find out IE1? 1 plus beta into IB1. So using this formula you can find out IE1. So now the currents of your input transistor is all known here. Now how will you find out the currents of your output transistor? That we'll see here. Okay, so now currents, how will you do that? IR1 plus IB2 is equal to IC1. We know that. IR1 plus IC1 is equal to IB2. Okay, so IR1 is basically what? Very easy. 5 minus voltage. 5. VC1 we know. VC1 is basically just a second. VC1 is also not known. Sorry. So 5 minus VC1 by RC1 plus IB2 is equal to IC1 basically. Okay. So now IB2, there is another way to find out IB2 is equal to IE2 by 1 plus beta. Okay, what is IB2? 5 minus VE2 by 1 plus beta into RE2. So what is VE2? Basically VC1 plus 0.7. VE2 is nothing but VC1 plus 0.7. Okay, fine. So because it is PNP, VC1 plus 0.7 is equal to IE2 basically. Okay, so 5 minus VC1 plus 0.7 by 1 plus beta RE2. Okay, so now so summing these two, basically IR1 and IB2, if you sum, is equal to IC1. So sum this one, 5 minus VC1 by RC1 plus 5 minus VC1 plus 0.7 by 1 plus beta RE2 is equal to IC1 is equal to, basically what you get is 1.12 milliampere, because IC1 is given as 1.12 milliampere. Okay, so with this possibly we can find out what is VC1, because RC1 value is known and RE2 value is also known and beta value is also known. So we can easily find out what is VC1. So this is how to solve the DC analysis of your multi-stage amplifier. Okay. Now apart from that, we can find out the IR1. We haven't find out what is the current through the IR1 basically. So IR1 is basically 5 minus, I have told you, 5 minus VC1 by RC1. So substitute the VC1 and you will get RC1 IR1 value, and then VE2 value also you can easily find out, and IE2 value also you can easily find out, because IE2 also 5 minus VC1 plus 0.7 that also can be found from here. And IC2 also can be found. IC2 is nothing but beta by 1 plus beta into IE2. Okay, that also can be easily found. And IR2 also, IE2 by 1 plus beta. So you will find this one. Okay. Then remaining node voltages, obviously we can easily find out. We know that VE1 is IE1 RE1. So we substitute that one, you can find. VC2 is also IC2 RC2. We can find it straight away. Then again VCE1. So VCE1 minus VE1, that will be your 2.26 volt. Then again VEC2, VE2 minus VC2, which is nothing but 1.67 volts. Okay. So now there is another problem is given to you. Design a bistable PNP transistor circuit to meet a set of specifications. I hope that this you can able to do this one. So anyway, I will ask you to go through this. This is again a same problem which we have seen earlier, except this is a PNP transistor. Okay. So I want you to go through this, and if you have any doubts, you come and ask. Come and ask me. Okay. Fine. I think this is we have already solved this one earlier. I think it looks like a repetition one already. We solved it already. Okay. Anyway, if there is any value change and other things and all, please go through it. It will discuss later. Okay. Fine. Okay, ma. So now let me take the another set of PPT just to describe you how the frequency response of MOSFET varies basically. How it is been done. We'll see this. Okay. What is the variation of this versus BJT? That's the two things that we are going to see today. Fine. So this is again module 1 only, so don't get confused with that. So in this case, they ask you to determine the unity gain bandwidth of an FET. I think this we have solved it in the class. 1 or 2 problems we solved, but remaining we'll see how to be done. Okay. Okay. So it's an N-channel MOSFET. So you have Kn value is given to you, and Vtn value is given to you. Lambda is generally 0 only, and CGD and CGS is given. So the formula that you have to use, and even VGS is also given. So if everything is given, it's a direct substitution. So GM is GM by 2 pi CGS plus CGD. Okay. So we need to find out what is GM. So GM is not it's not the way that you find out from the BJT. It's a little different because the transistor parameters are required here. So it is basically you can use this equation. I suggest you to use this particular equation for you. Okay. So it is GM is equal to 2 Kn into VGS minus Vtn. So Vtn is given, VGS is given, and 2 Kn you can easily find out 1.2 milliampere per volt. And FT is basically substitute this one, GM substitute, CGS and CGD if you substitute, you will get FT. Okay. Now the next problem is the parameters of an N-channel MOSFET are Kn, Vtn is 0.5 and lambda is 0, CGS is given, and CGD is given, and CGS is also given. So what we can do here is that we need to find, they are asking us to find out the transconductance and the bias current. Okay. Now how will you find out the transconductance here in this case basically? Because we need Kn is given to you, okay, Vtn is given, but VGS is not given. So, but there is another thing is that what they have given, they are given you FT. Okay. So what we can do is from this you can find out from this formula, first find out your GM. Okay. Once you find out your GM from this equation, okay, what is GM is equal to? GM equal to FT into 2 pi CGS plus CGD. So from this equation find out GM, is FT is known, CGS known, and CGD is known. And then once you have found that one, what you do, you substitute in this equation. GM is known, Kn is known, Vt is known. Find out VGS from here. Okay. Once you have done that one, then what do? You find out your ID, the bias current. Okay, ID is basically what? Kn VGS minus VTN the whole square. So this is known, this is known, and this is known. So you can easily find out the ID. So this is how you need to find out your ID current. Okay, fine. Okay, now go ahead. The answer is given to you, so you can see. Okay. Now the next question is determine the Miller capacitance and the cutoff frequency of an FET. So basically they ask you to find out CM and FT. So for the circuit 7.11 they say basically. Okay. So let us take this circuit. Okay, this circuit only. So what is your small signal model for this? Basically, I'll draw this for you here. Okay. So that's your small signal model of your MOSFET. Okay. So at the output side, what do you have? You need to basically open circuit this one, because we are going to find out high frequency analysis basically. So high frequency analysis, because you are finding out your CM is, obviously we need to know high frequency MOSFET only, high frequency model only. So that means output is short basically. Okay, output capacitance act like a short for you, and obviously your VDD will be ground, and this also short. Basically you don't have this resistor. Okay, so the output side you have RD and RL parallel. Okay, sorry, RD and RL parallel. RD parallel RL. That's my V0. This is basically GM VGS and VGS. At the input side, what do you have? You have R1 and R2 parallel, and with RI and VI there. Okay. So R1 and R2 parallel, and you have RI and VI. And RI. Okay, this is a mid band, but internal frequency, what do you do for your high frequency model? You basically have capacitance. This is CGS, and you have a Miller capacitance in parallel CM. So you have CGS and CM. So they are basically asking you to find out CM. CM equation is basically CGD into 1 plus GM RL. So CGD is known, GM is not known. GM, how will you find out? Basically, you have to do a DC analysis on this. Okay, do a DC analysis, convert the circuit like this basically. This is MOSFET, N MOSFET it is. And you will have that's your VDD, this is your RTH, this is VTH. Because when you're going for DC model, what do you basically have in your DC model? When you have a DC model, what we basically have? You will open circuit this capacitors, all this network will go. Am I right? All this network will go. So VTH, RTH, RT is nothing but R1 parallel R2. And since no current flowing through this, there won't be any drop. So we will have left with VS and VG. So find out VG and VS and find out VGS. So once you know that one, so what will happen? GM, how will you find out? GM will be equal to 2 Kn VGS minus VTN. So once you know this one, what you can do, you can find out VGD, GM and RL all known, so CM can be easily found. Okay, so VGD is not given in this one, I think so. CGD, so CGD will be given actually. CGD should be given. Look, you can take the CGD basically, 25 femtofarad. Okay, so substitute that one, you can find out straight away here. Is that okay? So that is all okay. Now FT is again very easy. It will become GM by 2 pi CGS plus CM. GM by 2 pi CGS plus CM. That's the equation that we have. So GM is known, CM is known, CGS is known, and you can easily find out the unity gain frequency. Okay, that's how we need to solve this problem. Okay, fine. Okay, very good. Now the next thing is that for the circuit given this, I think this is basically a problem for module 2, so I will deal with it later. Okay, so with this I am closing my module 1 with all the relevant problems solved, and probably in the class we'll try to solve more problems, and if not, I will add more videos on more problems, and then you guys go through it, and if you have any doubts we can discuss in the class. Okay. Okay. Thank you.